All right, good morning, everyone. First, and I apologize for all these virtual learnings that we've had to do. I can't control other people's schools. So hopefully once all the snow melts over this weekend, which it looks like it should, we won't have any more virtual learnings for the rest of the semester. But again, I can't guarantee that. So we'll see how that goes. But again, sorry for all that. But yeah, we got to do what we got to do. These things happen. So good. So let's continue our conversation we finished off with yesterday, and that is equilibrium. So again, we defined equilibrium as the sum of your existence is equal to zero, right? So basically means that the system is either moving at constant velocity, which means the acceleration has to be zero, or that it's completely stationary, so nothing's actually moving. So again, the acceleration is equal to zero. As far as Newton's laws are concerned, there is no difference between those two scenarios. So equilibrium just means either my cell phone here is moving at constant speed, or it's just sitting still. Either one of those is the same thing as far as Newton's laws are concerned. In both cases, the acceleration is equal to zero, so there is no distinction. But in equilibrium, all that means is the sum of the forces must be equal to zero. So we talked about this problem yesterday, but let's actually analyze it. So again, here I have a sign where that sign has a mass of 10 kilograms. That's attached to 3 cables. So we have this first cable here, which makes an angle of θ1, which is 37 degrees relative to the horizontal here. Cable 2 here, which makes an angle θ2 at an angle of 53 degrees. And then finally cable 3, which is kind of tied here. So as we mentioned yesterday, to solve this problem, what we have to do is actually break this up into 2 different pieces. So first I'm going to break it up into this yellow piece here. So I'm going to look at only the sign connected to this 3rd cable. And then again, I'm going to look at the knot here. So again, the knot is actually not really a physical thing. It's not actually a mass, but I'm going to treat it as a mass to then get a 3rd and 2nd equation. So as we talked about again at the end of yesterday, we said the reason for that is we have 3 unknowns, in that case, the 3 tensions. So we need 3 equations. So we're going to get 1 equation from the yellow section here, and then 2 equations from the sum of the forces in both the x and y directions for our little intersection here. So let's do that. So here, let's look at the mass. So at the sign, so here we know we have a weight. So we got mg pointing straight downward. We have a tension force pulling upward. So I'm going to call that one T3 in this case. And we know this is a static equilibrium, so nothing is happening. So the sum of the forces on this guy is equal to 0. So I'm going to just arbitrarily choose my positive y direction to be upward, just for funsies. So if I look at the scenario, I can then say, well, the sum of the forces in the y direction are equal to 0. So here I have T3 minus mg is equal to 0. T3 is positive because it's in the direction of positive y. Mg is negative because it's in the opposite direction. So this tells me that tension 3 is simply then equal to mg. So in this case, since this is 10, this is going to be 98 newtons. So this is the tension in the 3rd string. Good. So to get our other 2 equations, as I mentioned, we now have to look at this knot here. So let's look at the 2nd section, 2. So here, again, even though this is not a mass, we're going to treat it as if it is a mass. So we're going to draw a free body diagram relative to here. So we do that here. So on this side, since T3 is pulling upward, we know by Newton's 3rd law on the knot section here, T3 then has to be pulling downward. By Newton's 3rd law, those 2 things have to be equal and opposite. T2 is going to go along the direction of this portion of the string. So that's going to be T2. And then finally, T3, color haven't used it, we'll use red, is going to go off in this direction along the direction of this chord. So this is going to be T1. For here, let's put in our coordinate system. So I'm going to call this my x-axis. And then let's put the y-axis in the usual upward direction so that this is my negative x or negative y-axis this way. Okay, let me extend my x-axis here. So this here is angle θ2. Alternate interior angles are the same. So this θ2 here is the same as this θ2, which means that this is θ1. That's the same as this angle. Because again, anytime I have a bisecting line, this angle here is the same as this angle. All those beautiful things you learned in geometry and didn't know why. Now you know why. So good. So from here, we can then put on Newton's laws. So from here, let's do the, I don't know, x direction first. So let's look at the sum of the forces in the x direction. So again, sum of the forces in the x direction is equal to 0 since this is statics, right? So equilibrium, nothing happens. So in the x direction, I only have two forces. I have this portion of T2 here, and I have this portion of T1 here. So this portion of T2 is positive because it points along the direction of positive x. This portion of T1 is negative because it's in the negative direction. Because both of these are the adjacent sides of these angles, they're both going to be cosines. So I'm going to get a T2 cosine of theta 2 minus a T1 cosine of theta 1 is all equal to 0. So from here, what this says is I can find T2 if I know T1, or I could find T1 if I know T2, which in both of those cases, I don't know either one of them. So even though this is a useful equation, and it will be a very useful equation in a minute, it's not exactly useful because I don't know T1 or I don't know T2. Right? But I can find T1 or T2 from the sum of the forces in the y direction. So let's look at the y direction now. So in the y direction, I have what? This portion of T2 going upward. So that's positive. I have this portion of T1 going upward, which is also positive. And then I have all of T3 going downward, so that guy is going to be negative. So if I write this out, I'm going to have a T1 sine of theta 1 plus T2 sine of theta 2 minus T3 is all then equal to 0. Right? So this is my sum of my forces in my y direction. Now from here, what this says is I can find T1 or T2 if I know T3, which I do know T3. I know that's simply the mass of the, or the weight of the sine. So now if we use this expression here, I can actually then rewrite T2, for example, in terms of T1, plug that back into this expression to rewrite this expression entirely in terms of either T1 or T2. From there, I can solve for T1 or T2 and then plug it back into this expression to finally find the last one. So let's go ahead and do that. So Preston, which one do you like better? Do you like T1 better or T2 better?
I like T1 better.
Like T1 better, good. So let's solve this one for T1 and then we'll plug it in the other one. So let's do that. So this says that T1 then must then be equal to T2 times then the ratio of cosine of theta 2 to cosine of theta 1. So from here, I'm just adding this term over here, dividing both terms or both sides by cosine. So this is my T1. So now I'm going to take this T1 here and substitute it into this expression for T1 to rewrite this entire thing in terms of T2. So let's do that. So here, I'm going to replace T1 with T2 cosine of theta 2 divided by cosine of theta 1 times sine of theta 1. So all I'm doing is replacing T1 here. Plus now T2 sine of theta 2 is all equal to T3. Right? So I'm just adding the T3 to the other side. So I'm doing two substitutions simultaneously. So notice here, I now have a T2 here, I have a T2 here, so I can factor out the T2 and then divide by everything to finally find what T2 is. So let's do that. So I get a T2 then is equal to a T3 divided by, so let's do it this way. What's sine divided by cosine? Tangent, right? So this term here of the sine 1 divided by, or sine of theta 1 divided by cosine of theta 1 is actually just tangent. So this is cosine of theta 2, tangent of theta 1 plus sine of theta 2. Right? So this is T2. So T3 here we know is simply 98. So we plug in our numbers. So this becomes 98 newtons divided by cosine of 53, tangent of 37 plus sine of 37. Plug in my numbers. What I find in this case then is this works out to be about 58.98 newtons. Once I have T2, I can now take T2 and plug it back into here, and now take that 58.9 or 98 newtons times cosine blah blah blah, which then works out to be about 78.27 newtons. So this is now T1.
I got a question.
Sure, Preston.
So I kind of got confused why you had to use you couldn't just do it with the f of x. You had to go to the f of y and use that equation.
Oh, because if I use the f of x, So the thing here is I only know what T3 is. So since I know T3, if I use only f of x, T3 doesn't show up into f of x, right? So the only thing that's left here in the x direction is this portion again of, so this is T2x, and then this portion here of T1x. But the problem is I don't know what T1 is and I don't know what T2 is. So I have an expression, which is going to be useful because we use that into the next parts, but this is a relationship now between T1 and T2, but I don't know either one of T1 and T2. So I first would have to establish what either T1 is or T2 to then use this expression to finally get the other one, which is then why we had to go to the y expression, because the y expression now relates those two things to T3. So T3 is the only thing I know at this stage. I know T3 is 98 newtons. So now using both the y direction and the x direction simultaneously with now this relationship will allow me to get rid of either T1 or T2 to then solve for that expression. And then once I know T1 or T2, now I can go back to this expression and find the other one. Okay. So that's the only reason I need the y expression in this case, because I don't know T1 and I don't know T2. But you're absolutely right. If I knew T1, all I would need then would be the x expression to then find T2.
I see. So you use the other equation because it had T3, and then you just solved for T1 or T2 cosine. You had me pick, and then you plug that into the other equation.
Exactly. Exactly.
Okay.
Exactly.
That makes sense.
Good. Very good. Yeah. Just sleight of hand algebra. That's all it is. Makes it look more magical than it actually is. That's fine. Everybody doing okay? Any other questions? On it? So this is equilibrium. So we'll talk more about equilibrium in the future and mention that this expression here actually is not sufficient. But for now, this will be fine for us. So equilibrium, again, just means that our velocity is equal to a constant, which again means that the acceleration is equal to 0. So anytime the acceleration is equal to 0, Newton's laws say all the forces must be summed together to give me 0. So this is equilibrium. So good. So the last topic we need to talk about is what's known as centripetal forces. Oops. So centripetal forces. So remember what Newton's laws says is primarily the second law says that whenever I have an acceleration, I have to have a force, right? Or a force is what generates an acceleration. So anytime my system accelerates, there has to be at least one force in the direction of that acceleration causing the system to accelerate. I say at least one force because it could also be that I have multiple forces, just one of them is bigger, so it goes in the direction of the overall net force. That's what Newton's laws say. Right, so Newton's law says the sum of the forces, i.e. the net force, is equal to the mass times the acceleration. So the system goes in the direction of the overall net force. But again, Newton's laws basically imply that if I have an acceleration, I have to have a force, or simultaneously, if I have a force, I have to have an acceleration. So that brings us to what we talked about at the end of the previous exam, that's radial or centripetal acceleration. So remember when we had the radial or centripetal acceleration, which was given by v squared divided by the radius, or the radius times the angular velocity squared, or 4 pi times the radius divided by the period squared, sorry, 4 pi squared. This is an acceleration, which means that by Newton's laws, if I have an acceleration, I then have to have a force which is generating this acceleration. This is what Newton's laws tell me. So what this means is anytime I have something moving in a circle, for example, my keys, which are moving in a circle, there is a centripetal acceleration pulling it towards the center of my circle, which means there has to be a force pulling it towards the center of the circle as well. This type of force is what we call the centripetal force. By Newton's laws, what this means is all we're going to do is replace this acceleration here with the centripetal acceleration. So for centripetal forces, this expression still holds. The only difference is now we're going to write the sum of the forces is now equal to the mass times the radial acceleration. Which means if I wrote this out, this would then be equal to the mass times the velocity squared divided by the radius, or the mass times the radius times the angular velocity squared, or the mass times 4 pi squared times the radius times the period squared. So all this says is that anytime something moves in a circle, there has to be a force which is pulling it towards the circle, or towards the center of the circle. So again, if this is my circle, my object is here, has a mass m, my radial acceleration is towards the center, there has to be a force which is then pulling it towards the center. And this is what we call the centripetal force. Now, things to note about centripetal forces. There is no such thing as centripetal force by itself. So we talked about this at the end of yesterday. What this means is there is no fictitious force called the centripetal force that's going to come and cause you to spin around for no apparent reason. Okay? There has to be a real physical force that acts as the centripetal force, which means that, for example, if this was my keys, right, swinging around through the center here, you wouldn't say, well, this one has a centripetal force towards the center. Simultaneously, it has a tension force pushing it outward, right? So if I said something like this, and then there was a tension force pulling in this direction, this is completely nonsense, okay? What is true here is what's causing my keys to move through the center of the circle is the tension itself. In this case, my tension is the centripetal force. So in this case, my tension is the centripetal force. Right? So another example would be what happens when you turn your car to move through a circle. Right? So let's say I'm driving my car. Here's my car, moving in this direction with a velocity, and then I turn my wheels of my car and I want to move through the center or through a circle. Right? What is the object which is causing my car to move through the circle? So as it's moving through the circle, let's say it's now here, velocity is in this direction, right? I'm moving in a circle, so I have a centripetal acceleration towards the center. What physical force is acting as the centripetal force in this case? What carries me through the circle? So what is the actual force?
Would it be friction?
It's friction, good. What kind of friction? So we have kinetic or static friction.
Be static?
Exactly, that's right. So here, what I would have then is what? The static friction would be pulling me towards the center of the circle. So my static friction would be the centripetal force in this case. Okay? So again, if I drew something like, for example, I drew my car was here and I said, well, the centripetal force was this way and the static friction was this way. And then I said the sum of the forces was equal to 0. So the centripetal force minus the static friction was equal to 0. So this is equal to this. Mathematically, this works out to be okay, but conceptually wise, this is completely false. So what happens is there has to be a real physical force which pulls me through the center of the circle. And you're absolutely right, Jarrett. What's carrying me through the center of my circle when I turn my car on Lloyd, for example, is static friction. And we know that over especially this last week when we had ice and snow. If you're driving down a car and you have too much ice and you turn your wheel, nothing happens, you keep going straight. Okay? Or with too much snow, again, you turn your car, turn the wheel, you keep carrying off straight. So let me give you some other examples. Here, I have loose chalk inside of this bucket here. But if I take it and I spin it around and I do this, none of the chalk falls out of the bucket. All right. What is the centripetal force as far as the chalk is concerned in this case? So in the case of my keys, it was the tension. Okay. Tension and the strain. In case of a car going around the corner, it's static friction. As far as all the chalk here, which can easily fall out, what's keeping this inside of the bucket? Right? What's causing the chalk to move through a circle?
The force of your arm.
Well, that's what's generating the energy, but what's keeping the chalk itself? Because I'm only holding on to this part. So I'm not actually holding on to the chalk itself. So what's keeping the chalk moving in a circle?
It'd be the bucket.
Be the bucket, that's right. And the bucket gives us what we call the normal force. Exactly, good job, Jarrett. So the normal force, what causes the moon to move through a circular orbit around the Earth?
Gravity.
Gravity. Good job, Ruth. So these are all different forces, which are all centripetal forces. So the hardest thing about centripetal forces for most students to get over is the fact that it has to be a real physical force which is causing the centripetal force. So it's not a different force, it's not a fictitious force, it's not something new, it's a real force that we have seen thus far, but acts as the centripetal force. So again, when I'm driving my car, I turn the wheel, that is static friction, which is my centripetal force. When I swing my keys here, doing something like this, or even sideways, any of these different variations, it's the tension. Here, when I swing around the chalk, it is the normal force as far as the chalk is concerned. And then here, if I was holding on this part, if I was asking you about the bucket itself, you could say tension or my hand, whatever that is that's causing the force on here. If it's the moon going around the earth, it's then the gravitational force. If it is an electron orbiting a proton, it is the electrical force. So there's always some sort of physical force which is acting as the centripetal force. So again, let's make a note of that. So here, when we're talking about centripetal forces, there is always a physical force which acts as the centripetal force. So after that, once we identify what the actual centripetal force is, again, the only thing we have to do is when we solve Newton's second law, when we do the sum of the forces, we're simply going to replace the acceleration with the radial acceleration. That's it. This is the only difference. This is the only modification. Here, again, which centripetal or which radial acceleration we decide to use will depend on what it is that we know or we want. If we want to know the velocity, we would then simply use the first one. If I want to know the angular velocity, I would then use the second one. And if I want to know, or if I know the period, I would then use the third one. So from here, which one we decide to use will then just depend on, again, what it is that we know or what it is that we're looking for. So again, if we know the velocity or looking for the velocity, we would use the first. Angular velocity, we would use the second. Period, then we would use the third one. So other than that, everything stays exactly the same. We still have to do all of our sum of our forces. We still have to do all that stuff. We just replace the acceleration with the centripetal acceleration. So let's do a few examples. Okay, and let's kind of see how this works. So the first one we're going to look at is what's known as a level curve. So a level curve is when you're just driving down the road and you want to go through a circle. So if I'm driving down the road, so say here's my car, going say this direction with a velocity of v, and I want to drive through a circle of some radius r. Okay, so here is my circle, and this is my radius r. So here, this is going to be on flat land. So this is a top view of it. And then a front view, for example, would be just here's my car, my wheels on my car, and my velocity is coming outward. Say in this case, in this direction, here's my velocity vector. So in this case, I'm turning to the right. So here we know there's going to be a static friction pulling towards the center, thanks to Jarrett telling us, which in this case means our static friction is in this direction. Very good. So let's say here, let's give some numbers. So let's say I'm moving at 30 meters per second. And I want to move through a corner whose radius is 50 meters. So here what I want to know is what is the minimum coefficient of static friction that I need to be able to make it through this corner without sliding. So we want to go through the corner without sliding. So again, I'm moving at 30 meters per second. I want to go through this corner, which has a radius of 50 meters. And I want to know what is the smallest coefficient of static friction, which will cause me to move through this circle. Now, this goes to something we mentioned before. When it comes to static friction, remember, static friction can be anywhere between 0 and the maximum amount. So let's kind of recap about static friction. Static friction can go anywhere from 0 up to a maximum amount, or that maximum amount then is equal to the coefficients times the normal force. Now, whenever I'm doing a problem which is involved with static friction, there always has to be something in the problem which implies to me that it's maximum. If there is nothing in the problem which implies to me that it's a maximum static friction, I cannot assume that it is this. Okay? The only way I can assume that it is this guy is if there's something that implies it's maximum. In this problem, we have something that implies to us that it's going to be maximum, and that's this portion which says we're looking for the minimum coefficient of friction. This minimum coefficient of friction tells me we want to assume that Fs is equal to Fs maximum. Because what I want to do is shrink the coefficient so far that the static friction becomes the greatest amount that it can handle before it goes over to kinetic friction. Okay? So here in our problem, there's something that implies to us that we're looking at the maximum static friction by looking at the minimum coefficient of friction. Everyone okay with this? Another way, another variation of this problem would be, what is the maximum speed I could go through this corner? This is another variation we could have. So another variation would be as if we're looking for Vmax. What is the maximum amount of velocity I could go through this corner? In that case, again, we would assume that the static friction is maximum. Okay? So again, any problem that we look at, there has to be something there that implies to us we have maximum static friction, so we can use this expression. Otherwise, we would just have to find it from a force. So good, so let's do this problem. So here, what do we know? So here's our frontal view. So here we know the radial acceleration will be in the direction of the static friction, which means the only force acting on it in the horizontal direction here, so let's call that our x direction, will be our static friction. Any other directions, which we're going to need, we also know that there's a gravitational force pulling downward, and we also know that there's a normal force pushing upward. What color have I used? We'll use blue. So here's my normal force. So let's go ahead and call this our y direction. Now, again, I'm doing the y direction because, again, I need to know that normal force for the friction force. So let's do that. So let me redraw my diagram here. So here's my car. So again, we have mg pulling down in this direction. I got my normal force pushing it up from the ground. And I got my static friction pulling it through the center of my circle. And my radial acceleration is towards the center of the circle. So this is my x direction, and this is my y direction. Okay. So good. So here, again, we would just do the sum of the forces. Let's do the y direction first. Good. So is it accelerating in the y direction? Good, Preston. No. So no acceleration in the y direction. So Ruth, give me a force in the y direction.
Gravity.
Gravity, good. Positive or negative?
Negative.
All of it or part of it?
All of it.
Good. Very good. What's another force in the y direction? Jarrett, can you give me another one in the y direction?
The normal force.
Good. All of it or part of it?
All of it.
Positive or negative?
Positive.
Positive, good. So in the y direction, we simply have the normal force minus the weight is equal to 0, which means our normal force is equal to the weight. Good. So now the static friction is in the x direction. So now let's look at the x direction. So we know the sum of the forces in the x direction is equal to the mass times the radial acceleration. Right, because here the acceleration now is simply the radial acceleration. So this is the only modification I'm making here. Now here, since we know about the velocity, we're going to rewrite this then as the mass times the velocity squared divided by the radius. Right, because we know that it's moving at 30 meters per second. So we'll use the first one. Now from our picture here, the only force which is causing this thing to move through the circle is the static friction. So that means that the static friction in this case, again, is our centripetal force. Now, again, going back to what we talked about, since we're looking for the minimum coefficient of friction, that implies to us that the static friction must be maximum. So I can then replace the static friction with mu sub s times the normal force. From the y direction, we now know the normal force is simply equal to mg, so I can replace that as well. I'm going to move over here. So this becomes mu sub s times mg then is equal to mv squared over r. Here the masses are going to cancel, so I don't care about the mass. And let's solve this for the coefficient. So the coefficient then is equal to v squared divided by gr. Okay. Plug in the numbers, what I get in this case is this works out to be about 0.37. So my minimum coefficient of friction I need to make it through this particular corner at 30 meters per second, and a radius of 50 meters is 0.37. That's my coefficient. Remember, coefficients always are dimensionless, so this has no units to it. Always okay? And again, just a nice little dimensional check. This is a velocity squared, so that's a meter squared per second squared. This also should be a meter squared per second squared. So remember, g is meters per second squared times a meter, so that's a meter squared per second squared, so the units do cancel. So just make sure everything works out properly. Good. So good, so this is what we call a level curve. Another type of example is what's called a banked curve. So let's look at a banked curve. Another good example here. So what's a banked curve? So a banked curve is a curve that is banked. Looks something like this. So this is a banked curve. So a banked curve is simply a curve which is at an angle of theta. Right? So in this case, here would be my car on a curve which is angled. Right? So what's the point of a banked curve? Is anybody here watching NASCAR? Yeah. So if you look at the corners in NASCAR, they're always banked, right? So why is that? Why do we use a banked curve in NASCAR? What are they trying to do?
Trying to keep the cars moving fast when they turn.
Exactly. The reason for that is now you can actually go through this corner without friction. So the point of using a banked curve is you can actually go through this corner without using friction. And what's going to carry it through the corner is actually gravity itself. So gravity is what's going to carry it through, but not explicitly through gravity, but it's actually through the normal force. We'll see that in just a second. So exactly, you're exactly right. So if it's gravity that can actually pull me through the corner, then I can go even faster if I take friction into account as well. So I can also use friction to help me go through the corner even faster to make sure that I don't have to go anything slow. I can still go through a corner at like 200 miles an hour. Right? This is what we do in NASCAR. Life is fun. So this is the point of a banked curve. The banked curve is to be able to go through a corner without actually having to use friction. But if I have to use friction, I can even go faster than I could on a level curve because I couldn't go through the corner as fast. This is why we actually use banked curves. So how does this one work? So let's draw a free body diagram for this guy. So what forces are acting on my car here? So if this is my car, so let's arbitrarily say my car is going, I'll just keep it in black. Let's say it's coming towards us in this direction. So this is my velocity v. So what forces are acting onto my car here? So give me a force. Teddy, can you give me a force on that car?
Force of gravity.
Good. Which way is that?
Pointing straight down.
Good. So mg, good. And Brooke, what's another force?
The normal force,
Normal force. Good. Which way is the normal force go?
perpendicular to the plane.
Good. So up in this direction, our normal force. Now, in this problem, we're going to be interested in going through the corner without friction. Okay. So basically, these are the only two forces which are going to be acting on our system. Okay. So we're going to look at this without friction. So I'll give you some numbers here in just a second. But let's say this is what we're looking at here. So these are here, and we're going to go through this without friction. We'll talk about how friction would change this problem if we used friction. So good. So good. These are the only two forces which are acting on it. Now the question then becomes, what is the direction of the radial acceleration? So if I want to go through this corner, right, where again my car is coming at me, and I want to go through this corner as fast as possible, what direction is going to be the radial acceleration? So meaning I want to go through the circle, right? So basically, if I'm going this way, heading towards us, that means the center of my circle is somewhere over here. Right? So this is the center of the circle. So my question then becomes, what is the direction of the radial acceleration for this thing to make it through the circle? So what do you think? What is going to be the direction of the acceleration? Should it be up the plane or down the plane or something in between? What do you think? So what would be the direction of my radial acceleration? Paige, you want to give it a shot?
I think it'd be towards the center of the circle because it's accelerating in.
That's right. It's exactly true. So since I wanted to go through the circle, what I want is my car not to slide down the plane. I don't want it to slide up the plane. I want it to stay at the same exact horizontal position that it's at. And as Paige said, which is exactly right, what I want it to do is actually just point to the center of the circle on the same horizontal line. So this is going to be the direction of my radial acceleration. Good job, Paige. So good. So from here, what this means then is what? So if I draw my x direction in the direction of the acceleration, draw my y direction point up this way, then this angle here, theta, is the same as this angle down here. Right? This is what Brooke was asking yesterday. So in this case, what actually acts as the centripetal force is not technically gravity, but it's actually this portion of the normal force. So it's actually the sine portion of the normal force, which is acting as my centripetal force in this case. Now, of course, that's going to be proportional to the gravitational force, which we'll see in a second. But here, my centripetal force, whoops, my thing backs up, is actually going to be equal to n sine of theta. So it's actually going to be the normal force itself. So good. So good. So let's analyze our problem. So here, let's do the sum of the forces in the x direction. So the sum of the forces in the x direction, we know it's accelerating. That's just going to be MAR. And here we know that this is going to be the sine portion of the normal force. And against the sine portion, because I'm looking for this little portion up here, that's pointing this way. So this is our NX. But again, this is the opposite side of that angle. So this is the sine portion of him. Right? That's n equal to MAR. Now from here, since this is the normal force, we have to get rid of the normal force by simply looking at the sum of the forces in the x or the y direction. So this is the sum of the forces in the y direction. Now in the y direction, it is not accelerating. So here we can say that this guy is equal to 0. So in the y direction, I have n cosine of theta, because I'm looking at this portion now, minus then the weight is equal to 0. So from here, this says that the normal force is simply equal to mg divided by cosine of theta. Substitute that in here. This becomes the weight times sine divided by cosine. But what's sine divided by cosine? Tangent, as Briston already told us earlier. So here the mass cancels out. So finally I get g tangent of theta is then equal to the radial acceleration. So let's actually put this into a problem. So this says I have a banked curve in the Daytona 500, which is at an angle of 31 degrees with a maximum radius of 316 meters. So here I have theta is equal to 31 degrees, and we have the radius of our circle is equal to 316 meters. So what I want to know then is, what is the speed that this car can go through without using friction? So what is the velocity equal to? So I want to know, how fast can this car go through the circle without this thing necessarily needing friction? Okay. So this is what we want to know. So how fast can I go through the circle without needing friction? So good. So now that since we know we're looking for the velocity, we're going to rewrite AR as simply v squared divided by the radius. So from here, we solve for the velocity. So this is the velocity then is equal to the square root of g times the radius times tangent of theta. Okay, so it's equal to the square root of 9.8 times the radius, which is 316 meters, times tangent of 31 degrees. Plugging in our numbers, we find is this works out to be about 43.14 meters per second, which is roughly about 80 miles per hour. So at the Daytona 500, my car can go through the corner at about 80 miles per hour with never needing to use friction. Now, let's talk about some interesting things about this. So the first interesting thing is notice this doesn't depend on the mass. So what does that mean? So that means that whether I was driving a little car or a tank or a big car or a Hummer or whatever, it doesn't matter what it is, this velocity, V, would be exactly the same. So whether I was driving a sports car or a tank or anything else, I could go through this corner at 80 miles per hour with the same effect. It does not depend on the mass, which is actually rather interesting. The other thing about this is what happens if the velocity I'm traveling is less than the speed? So let's say the actual velocity I'm moving, so my actual velocity is less than this velocity here. So let's say I was driving my car at 60 miles per hour instead of 80 miles per hour. What would happen to my car? So if it takes 80 miles per hour for my car to go through this circle so that a centripetal acceleration is directly towards the center without using friction, but if I was actually doing 60 miles per hour instead, which is less than this 80 miles per hour, what would happen to my car? What would my car want to do?
It would go down the slope.
Exactly. It would want to slide down the slope. So if I'm not moving at enough speed to keep it at the same horizontal position, it would actually want to slide inward towards the center of down the slope here, which means that to keep it from sliding down, what would have to be the direction of the static friction? It would have to be in the opposite direction, which means it would have to be pulling upward. Okay. So notice that here, if my speed was less, then my car would want to slide down the plane. Which means that we need static friction acting up the plane to keep us from sliding down. So in this case, what would happen then is we would have to modify our free body diagram. So let's talk about that. So what would happen now is we would still have the normal force perpendicular to the surface. So this would be our normal force. We would still have weights pulling down in this direction. But the difference now is we would have to have a static friction pulling us up the plane. This would be the difference. So for example, when you're driving on a banked curve on the road, so let's say, I don't know, you're going down Hogue. Hogue has a lot of turns, right, on the way to USI. There's some turns that are banked and they rate the corner at a particular speed. Now, if it's a banked curve and they rate it at a particular speed, what that means is that's the speed at which you can go through that corner without having to use friction. So let's say that it's a nice snowy day and you're going on a banked curve on Hogue and it says you can take that at 30 miles per hour, but you decide, well, it's snowy, so I'm going to go slow. What's going to happen to your car? Well, based on what we just talked about, it's actually going to slide down. You're actually going to slide down into the ditch because you went too slow. So you thought you were being safe, but you're actually not being safe by driving at the speed at which it is they told you you should not be driving. So good. So what would happen then if you went too fast? So let's look at another case. What would happen if your actual speed then was greater than this velocity? So let's say you were doing 100 miles per hour instead of 80 miles per hour. What would happen in that case? What would be the direction your car would want to slide now?
Up the hill.
We want to go up the hill now, right? So in this case, it would want to slide up the plane, which means that we would need static friction then down the plane to keep it from sliding up. Cool. So in this case, what would happen then is our free body diagram look like this. So again, I would have normal force this way. I would have mg this way. But now since I'm moving too fast, I would need static friction pulling me down to make sure that I stay. This is what actually happens in Nascar. So they're not going to take that corner at 80 miles per hour. They're going to take it at much faster than 80 miles per hour, which means that now they need static friction pulling down to make sure they can go as fast as possible. Good. How much time we got? Okay. Everyone's okay? Not too bad. Good. So a couple more things to look at. Next one we're going to look at is what's known as a vertical. So let's look at a vertical circle. Probably won't finish this one today. We'll pick up with this on Monday, but it'll be fine. So what's a vertical circle? So a vertical circle is exactly what I was doing with my keys here. It's just something which is moving vertically, right? So in this case, my keys are swinging in a vertical sense, right? So let's draw this scenario. So here, the two interesting points we want to look at is when my keys are on the bottom of the circle and when my keys are on the top of the circle. We want to see what's the difference between those two scenarios. So let's say here, I want to look at when it's up here. Let's call this A. And I also want to look at when my keys are down here. Let's call that B. So good. Let's look at A first. So my keys are swinging and they're in the bottom position down here. What forces are acting on my keys? So remember, this thing is swinging. So at this point, it has an instantaneous velocity going this way. So it has a centripetal acceleration going upward. So let's draw those two things on here. That's why I use the right thing to draw. So let's say here, my velocity is moving in this direction. So I have centripetal acceleration moving upward. So on my keys, what are the forces which are acting on my keys?
Tension.
Good, I got tension. Which way is tension?
Up.
Upward, good, towards the center of the circle. And what else?
Gravity.
Gravity, good. So gravity is just pulling straight down. Good. So in this case, it is actually the difference between the tension and the weight, which is the centripetal force, right? And I can see that by, if I look at part B, so let's call this my Y direction here, since centripetal acceleration is upward, say the sum of the forces in the Y direction are equal to MAR. So here I have my tension upward, so I get T minus my weight is then equal to MAR. Now, what if I'm looking at A, right? So now if I'm looking at A, now I have my velocity is pointing in this direction. So it's my velocity V. My centripetal acceleration is towards the center, which means in this case, it's pointing downward. Right? So this is my centripetal acceleration. So now my keys are here, right? So what forces are now acting on my keys at this point?
Tension and gravity still.
Good. So I still got gravity downward. I still got tension, but what's the direction of tension now?
Downwards.
Good. So tension is now pointing downward, right? So this is my free body diagram here. So what happens here then is now if I'm looking at point A, so for A, I'm going to take Y direction to be downward because that's in the direction of the radial acceleration. So I'm now going to say that some of the forces in the Y direction are again equal to MAR. But now I have the tension plus the weight is then equal to MAR. So down here, it's actually the difference between the tension and the weight, which is the centripetal force. But up here, it's actually the sum of the tension and the weight, which is the centripetal force. Now, what happens then to the tension? Well, if I solve the tension down here, I get the tension then is equal to what? Mass times the radial acceleration plus the acceleration due to gravity. And if I find the tension up here, the tension then becomes what? Mass times the radial acceleration minus g instead. So one big difference then between when it's down here versus when it's up here is that the tension reduces, right? So what happens is as this thing swings down, as it starts moving downward, the tension in the strain gets bigger and bigger and bigger and bigger until it reaches this point. When it reaches this point, it reaches its maximum amount of tension. Then as it swings up, the tension is going to reduce until it reaches all the way up here, where it then reaches the lowest amount of tension that it has. So as it actually swings through in a vertical system, the tension is constantly changing within inside of the strain. Now, another example of this would be if you go on a loop-to-loop in a roller coaster. Right? When's the last time any of you have been on a roller coaster? One that goes through a full circle? Been a while? So if you remember back to the last time you were on one, what do you feel? So if you go through a loop, when you reach the bottom part of the loop, what happens to you in your chair?
Raise up.
Goes up. You kind of feel like you're being pushed down into it, right? So what happens is that normal force that's pushing on you between the chair and right? Your butt is now increasing because you're being pushed downward. Right? And that's the same thing that's happening here with the tension. What happens when you reach the top point? What happens in that case to the normal force? So remember back all those years ago, last time you were on a roller coaster. In that case, the tension becomes really small and you actually borderline fall out of the thing. Mm-hmm. So what actually happens in that case is the normal force will eventually go to 0. So if it's not moving at a fast enough rate, you will actually be borderline falling out of the actual roller coaster. So the point of all that is, what I'm trying to get at is here, when I'm thinking about my keys, there is a minimum velocity that I need for my keys to actually make it through a full circle. If I don't give it enough velocity, these keys will never make it through a full circle. Right? So I start off down here, give it a velocity, but that velocity isn't enough, they will never actually be able to make it through the circle. But if I give it enough velocity, it will just make it through the circle. And then if I give it too much velocity, what happens then is that the tension will just keep increasing. So for any time I have something which is moving through a vertical circle, there has to be a minimum amount of velocity for this thing to make it through the circle. The minimum amount of velocity for this thing to make it through the circle corresponds to the fact that when it reaches its maximum point, I want the tension to go to 0. Which means that what's going to carry it through the circle is not the tension, but it's the weight itself. This is the same thing that's true with a roller coaster. So anytime you build a roller coaster, you want to go through a roller coaster, you need a minimum amount of speed for those people on the roller coaster to make it through the loop. And that happens when the normal force between the roller coaster and the person's butt is actually going to go to 0. This is the minimum amount of speed that you need to make it through. All right? So, and again, we can see that from here. So in this case, the minimum amount that tension can be would actually be going to 0. Okay. In this case, this will then give us the minimum amount of speed at which we would make it. So for my keys, the min corresponds to the tension going to 0. So when this happens, I have 0 then is equal to the mass times the centripetal acceleration minus the gravitational. So this is equal to 0. I can get rid of the weight, or the mass anyways. So this gives me my radial acceleration is simply equal to g, which means that v squared divided by the radius is equal to g, which means that the minimum velocity to make it through the circle, as far as my key is concerned, or again, being on a roller coaster, is the square root of g times r. So this is the minimum amount of velocity we need to be able to make it through the circle. This is something that's going to come up a lot in the future. Okay, make it through the circle. All right, I actually went overtime. Sorry about that. So we have one more example to do after this, but we'll do that on Monday. So again, we'll finish this stuff off on Monday. So we'll do one more example. And then from there, the rest of Monday, we'll review for the exam. Because again, when the exam is moved to Wednesday, and then I'll break out all the group assignments and let you guys work on the group assignments the rest of the time on Monday. Okay, so basically, we're almost done with everything. Other than that, I did post conceptual questions. Those are due tomorrow. I'll also send out an email about that. What's up?
Well, no.
Gotcha. It's iPad right now. Okay, so I have all these things here. So anyways, I'll see you guys on Monday. Have a good weekend. Hopefully all the snow melts and we have no problems getting there on Monday. So life will be great.
But I don't want
Have a
it
good
to
one.
come out so I can collect more ice crystals.
Oh, I see. Ice crystals are great. Okay. Bye, everyone. Bye.